Shall I start? Yeah. Okay. So hi, everybody. It's nice to see some familiar names and maybe later even some familiar faces. So I'm going to talk today about evidence and ontologies and language models in managing evidence, broadly speaking. And what is evidence? It's in the context of medical or clinical or health-related research, mainly means publications. It can also be data sets or some other kinds of evidence that can be produced. But mainly the problem for management of evidence is that there are a lot of publications. And I really like this illustration. This was a real human artist, not an AI generated art, although you could imagine similar AI generated art these days, which is showing this kind of monster of publications running away from who's trying to sort of catch it. And the numbers here are quite staggering. So on average, you have something like 1.6, 1.7, 1.8 million articles added to PubMed. So PubMed is a big database of medical literature, relevant literature, every year, which means 4,000 plus articles per day. And of course, for any one specialty, you may not be interested in everything. Of course, nobody is trying to read this whole body of literature, but for nevertheless any one topic or question, there are actually more publications than anybody human can read. And I will show some numbers for specific topics a little bit later on, but some recent evidence sort of looking at how long it actually takes to answer a question based on getting an overview of the literature has computed that efforts that try to do this with a so-called systematic review, where you start out, okay, I have a question, now I'm going to look at all the literature, try and get all the literature that's relevant to answer this question, and eventually get all the information out of that literature and answer it. Some evidence shows that this takes itself more than a year for any given one question on average. So 1.25 years, and we see that also in our research, that it just takes a really long time. There are various different interrelated problems for why it takes such a long time. And I want to speak to two different aspects of that in this session. And they will talk to two different types of things we can do to try and mitigate this problem. So one aspect I want to talk about is, of course, the ontology aspect. And here I want to focus on the importance of shared definitions, which is already important for defining a question and for sort of deciding what parts of the evidence are relevant to answer that question. And here I just want to bring a kind of thought-provoking story to set the scene, or two thought-provoking stories. And one is, okay, let's imagine we're trying to answer the question, any question related to evidence about tobacco use is an important public health problem, one of the biggest risk factors for cancer. So we're trying to answer questions about tobacco use. Now we might want to ask, okay, is tobacco use going up or going down? This seems like a kind of easy question to answer with some national or governmental statistics. And here you see some quotes from the Center for Disease Control of the US. I'm just taking numbers from the US because they were easy to find, but also because of definition-related aspects, which will be revealed shortly. So you see here in 2019, 20%, in 2021, 18%, in 2022, 19%. So this doesn't look like a decrease is happening, at least over these 3 years, which have been reported. Now, from a different source of, do we maybe have some background noise or, okay. Okay, so from a different source of statistics, you actually see different numbers. So you see here fallen 73% from 1965 to 2022, and even over the last 5 years, fallen 70%. Yeah, maybe can we have everybody muted because I'm getting a terrible echo, which is...
There is one person, Jay Charlotte.
I think from your key, you can mute him or them.
Yes. No.
Okay, yeah.
Now it's good? Now it's good. Okay, so I just, sorry for, it's super difficult to concentrate when you hear just a second later an echo of everything that you said. Anyway, so the point is that you see this kind of contradiction here. They're saying here by the American Lung Association that these rates are falling, and you see this CDC saying reporting more or less constant percentages. And of course, these are reported in different ways, but there must be a quite dramatic difference to account for this kind of very different messages. And what accounts for this difference, actually, maybe some of you already guessed just from looking at these descriptions, but the important thing that you need to focus on is what are they actually reporting statistics of, right? So here, these ones used any tobacco product, and here you have smoking. These are not the same thing, and actually smoking is defined as combustible cigarette usage or combustible tobacco usage, while used tobacco product is defined in such a way in the US that it incorporates also the use of e-cigarettes that contain nicotine, so alternative nicotine delivery systems, which in fact have a very different safety profile and should be, from a health perspective, treated very differently. But they're included in these numbers, and actually in a lot of US-based tobacco-related research, they're kind of lumped together under this definition of used a tobacco product, which makes it very difficult to figure out from the research literature, actually, which are the sort of dangerous or health-related uses and which are not, or having a different safety profile. So definitions matter. We as ontologists can all agree that definitions matter. And definitions can be peculiarly hard to kind of figure out from to answer a given research question. So here's another example. This is from a systematic review where we aimed to, in the context of a project which is really trying to get answers about effective interventions in a mental health context. The overarching question was about the mechanisms through which exercise reduces symptom severity in post-traumatic stress disorder. So that's a kind of very specific, but the general idea is, okay, exercise, very good for the health, also good for mental health. This is known, but then there are specific ways that exercise might supplement other treatments like psychotherapy and so on. And there's, of course, a big interest in figuring out when does it help, when doesn't it help, how do you use these different things together for maximal benefit for the patients. And these were some of the types of things that this review was aiming to answer. Now, when you are doing such a review, you have to go and read a whole lot of literature and figure out, is this literature giving you some information to answer this question? And for this, you define what are called study inclusion and exclusion criteria. And there you go in and sort of say, okay, we're interested in studies that did this type of exercise together with that kind of intervention. And at the end of the day, you have to decide, is this study going to help you answer the question? And here you see the study inclusion and exclusion criteria for this particular study. And what you see here, okay, exercise will include anaerobic, okay, resistance and strength training, aerobic exercises, exert gaming, that sounds fun, active stretching, before, during, or after the psychotherapy, etc., etc. Then the exclusion, it says we will exclude Pilates, martial arts, yoga, Tai Chi, and horseback riding. This is quite a strange exclusion criteria list. And in particular, what caused a kind of challenge here is this idea of we will exclude yoga, Tai Chi, but these are very similar for anybody who's not an exercise specialist or a specialist in these areas, very similar to active stretching and this kind of thing. So how do you really tease them apart? But the rationale why the researchers wanted to set it up this way is that yoga and Tai Chi and maybe other martial arts and other of these types of things, they may have other psychological benefits in addition, because you're sort of giving a whole package, a yoga package, in which you're being given maybe some mindfulness exercises, maybe some additional things over and above the physical exercise. But this is very difficult to sort of, you can see how subtle and nuanced it is. In order to get out the mechanisms by which exercise sort of supplements psychotherapy and improves mental health, you need to cut out a whole big chunk of actually what is exercise. So definitions matter and consensus is hard, and building up an overview to answer any one question is actually, you can see or get a sort of feel for why this takes a really long time and is really difficult. So ontologies help with this problem. They help in various different ways. They help, first of all, by kind of centralizing and coordinating definitions around all of these different things we've been talking about: tobacco use, yoga, exercise types, and so on. And they also help because you can kind of set up a system in which you do this work once, of doing the hard work of defining when does it matter whether the exercise does or doesn't include a mindfulness exercise at the same time. And you can then specify all of those kind of things as shared definitions, which are then attached to data in the right way. And of course, many of you will have already heard about the gene ontology, which is doing this kind of work on a large scale for molecular biology. And there are various other ontologies. I worked for quite a while on a chemical ontology, which is widely used for bringing some kind of order and classification to the world of biologically interesting chemistry. And more recently, and more related to the examples that I was just giving in the beginning of this, we've been working on ontologies for the domain of behavior change and for addiction, and in general for the social and behavioral sciences. And here in particular, the Human Behavior Change Project was a large-scale project to kind of map out the landscape of human behavior change and develop an ontology. For that landscape, the behavior change intervention ontology. And this has now been extended to the Apricot project, which has been funded by the NIH for 5 years to extend and develop tools and resources for. So the Apricot actually stands for Advancing Prevention Research in Cancer through Ontology Tools. So prevention research encompasses behavior change, because one of the best ways we can prevent cancer is by getting people to stop smoking and so on. So in this context, in terms of ontologies and ontologies defining things, I think the interesting thing is quite how specific and how detailed ontologies have to be in order to really capture those subtle nuances between defining one kind of thing or another kind of thing. And here's another example. So this is taken from the behavior change intervention ontology that's been developed for this project, this big project. This is the online web interface where you can browse the ontology and search and look at the definitions and so on. And this is a kind of example of a social support behavior change technique. Social support is considered to be helpful in helping people to change and sustain changed behavior, because you have some, it's been shown to be quite effective. It's an effective way of intervening. People respond well to social support. And social support is often mentioned in publications. Yes, so we set up this behavior change and people were given social support. But it's not necessarily specified in the publication what kind of social support was actually given. And here you see that if you really do the sort of conceptual analysis and break it down, there are actually lots of different ways that people can be given social support. For example, they can have support along a sort of dimension. Is the support emotional? Is it informational but provided by a different person, or is it really instrumental? Has the social support involved the person actually helping or doing something for them, like going shopping for them? And then there are different, another dimension, which is, has the investigator, because we're talking about research, so usually there's a kind of study provider, have they given the social support, or have they just got somebody else, maybe a family member, to give the social support? So is the support delivered, or is it arranged, or is it just advised, which seems like quite far removed from the actual social support which happens in the end? So typically, researchers don't present their interventional content at this level of detail. But actually, these distinctions matter in terms of determining effectiveness. And having an ontology which kind of prompts people to think, is this what they're doing or that what they're doing, and really describe it at the level of detail that's needed is a very useful and valuable thing. So the behavior change intervention ontology contains many different branches to describe different aspects of interventions at that level of detail, including modes of delivery, which means how was an intervention delivered. Could be delivered by a person or by an app or by a leaflet and so on. Behaviors, of course, are the most important focus area of the behavior change in a way, and you can describe and classify behaviors in a lot of different ways. Human behaviors are very flexibly defined, and it's quite a challenge to come up with an ontology, especially to sort of have a classification hierarchy where the classification is always true of the behavior. So it's, for example, walking, you can describe what the person is actually doing when they're walking and what the walking behavior is, but you can't really call it a health-related behavior because it's not always a health-related behavior, right? A person might be walking despite the fact that they have a twisted ankle and they're only walking because they need to get to work or something, and then you wouldn't usually call that a health-related behavior. But anyway, that's the challenge with classifying. One of the challenges with classifying human behaviors is the kind of context dependence of these categories, which we often use in the research literature. Another aspect of thinking about behavior change interventions and interventions more broadly is this concept of mechanisms. So mechanisms are causal processes through which the intervention could be working. And in the case of behavior change interventions, there's a big focus on mental processes. So typically it's kind of having a psychological causal mechanism when something works to change people's behaviors. Not always. There are also environmental or somehow external mechanisms which could also result in changing behavior. But a big focus of this branch of the ontology is really on mapping out the different psychological processes that could be involved. So then, just in terms of the application, like how is this actually used to help solve this problem of getting an overview of the evidence? We have developed a kind of database of evidence which has been extracted from study reports and which has been mapped to ontology values. So the different things that are captured in the ontology can be associated with the data in this database. And here you have different annotation types. So for example, you can have annotation while something was mentioned in the literature, was present or absent, but you can also have values that you're extracting. So your annotation might be the country, but then the country is actually named, and that gives you a list of, I don't know, how many is it, 200 different countries. Or you could have quantitative values that you're extracting, something like an age of a population or a mean age of a population. There you've got an ontology class, but you've also just got an sort of a statistical type for this number and the number itself. And then all of these different values and categories are stuck together in this database, and we've used that to build a kind of prediction system. In this case, to predict smoking cessation. So that was our first use case. And this, I think it's not fully related to the overall topic of the talk of sort of how can ontologies be used to build consensus. but I think it's a nice description of an applied use case of this kind of ontology system. So what you see here is that we've got this prediction tool, which behind it has a kind of a trained predictive model. And the model is based both on the ontology and on the data, which is extracted from the literature. And you can specify aspects of the intervention which were applied. You can specify age and so on of the population. And then it gives you a prediction for how that intervention, based on the data, how the output might be. So you could specify, it doesn't have to correspond to an actual intervention that is in the database. You can specify hypothetical scenarios. And that's a way for people to sort of get a more tangible output from the data set than just to understand what has been studied, even though usually evidence management is about understanding what has been studied. So, but this is just a useful kind of application of the ontologies and the data set applied to the use case of smoking cessation. And we do plan to extend that also to physical activity, in the near future. So another thing that makes it so hard to integrate evidence and to build consensus over and above the sort of conceptual difficulties of really figuring out what people are talking about in their papers and being clear and specific about that in a shared way, which is the part that ontologies are really good at and help with. The other aspect is really just the numbers aspect. And here it's even for very specific questions, which you might want to answer for a given project, you have simply overwhelming numbers of publications which you need to look at. So another project which I'm involved in, which was having this more mental health focus, which motivated the example I gave earlier with the yoga and the exercise, is called Galenos. This project, Galenos stands for Global Alliance for Living Evidence in Anxiety, Depression, and Psychosis. And living evidence here just means that the objective is to answer questions over the whole of the evidence and then keep those question answers up to date in a living way, to continuous basis. Do you still hear me? Somebody nod?
Oh, yes.
Yes? Okay, good. Because I got an error message for a second there. Okay, so then I carry on. So here what you see is a data set of literature extracted from a database called OpenAlex, which is like a database of publications. It's a bit bigger than PubMed. It's not focused only on medicine, and it's open access, so you can query it and extract all the information from it. And so here you see the years, kind of publication years, for 10 years, 2014 up to 2024. And there's a spike in January of each year. There's just artifact. It comes from publications which are included in the database, but for which the month is not known. And the query here is anxiety or depression or psychosis. This is like the topic area of the project. And then various other parts of the query which are looking for sort of, it's focused on a treatment or a therapeutic or a mechanism or early intervention or diagnosis. So these are the things that this project is interested in. And here you see that over this period of 10 years, there were 252, this query returned 252,000 papers. And that means that on average, you're looking at 63 per day. So it's really, even for this more focused and more specific, okay, you can get much more specific than that, but this is one project where there are, say, 3 or 4 people employed to kind of try and make sense of this literature. And yeah, you can just see how quickly this becomes completely unmanageable. So there is a really strong need for automation in this area, for automated computational approaches that are able to kind of say, okay, let's get as much as we can automatically, and then we can go on and get the humans to look at the most relevant parts that humans have to look at, but let's automate as much as we can automate. And in this area, of course, language models have emerged in the last few years as a really key technology to solve or to address this challenge. Language models we're by now all familiar with. They're systems like ChatGPT. They're trained on a whole lot of language as their sort of medium, and then they learn from all this training data something about how to interact with the language, something about how to extract and retrieve and process information from language, and even how to produce information in well-formed language. And this is such an exciting and obvious application area for language models that actually by now there are probably more than 20 or 30 different applications that have already said they can accelerate or even do completely evidence management with language models. So here's one which is more academically oriented. Storm, get a Wikipedia-like report on your topic with AI. GPT researcher says, say goodbye to hours of research. This is good, right? We could all use some more hours in our life. Consensus, this is, I think, quite a relatively good one. It offers some nice features. Notice the name, consensus, right? Here we're really doing exciting things. AI search engine for research. Undermine says radically better research, radically faster. Now I'm starting to feel a bit insulted, right? What was wrong with my research? I thought it was kind of good. I'm not sure it can get radically better. Cite AI for research. Elicit, analyze research papers at superhuman speed. Okay, fair enough. Superhuman speed is probably not hard if humans take a year and a quarter to put together a whole lot of research papers. But you get the idea. A lot of claims, a lot of companies, most of these are for profit. Some of them are more academically oriented. And they're all claiming to do this thing that we've seen is very difficult and takes a very long time for humans to do. And of course, the question emerges, okay, yes, there is a technology now, this language model technology. It can process language. It can do things with language. But can it really do the thing that we need it to do? I think this is the important question, right? Can it really answer those subtle questions or make meaningful data sets out of literature in the same way that an expert human would do? And I think for this, there's a great deal of skepticism about the capabilities, despite those kind of large claims which people were making in the previous marketing taglines. So here is an article which was written by experts in the field of systematic reviewing, so experts in evidence management. And you can see some strong skepticism, despite the fact that many of these people who contributed to this article actually do work in the field of systematic reviewing automation themselves. So they do actually apply these technologies. So here you see a kind of very deflationary quote. So this guy says, I'm sure we'll get there. So this idea of full automation using this technology. I just can't tell you whether that's 10 years away or 100 years away. So definitely not sort of having that same level of confidence that it's already happened. So what gives between this kind of very optimistic sort of sales pitch and then this much more skeptical expert view? And I think here it's really the details make the difference, right? If you put together in some way a whole collection of literature is really not the same thing as doing a systematic examination of literature. And one of the things that people are doing when they're doing that systematic examination of the literature is they're asking themselves, what kind of definition did this study apply? Were they using the same ontology or a different ontology? How do we match those definitional systems up together? And then you sometimes have to kind of almost redefine, you know, a lot of the research results in order to put them together in a consistent way. And these language-based systems by themselves are not doing that yet. That's just not what they're doing. They're sort of taking a much more agnostic perspective and just saying, okay, what was written is what was reported, that was it. they're not critically engaging with the conceptualization of the literature. So I'll try to go a little bit quicker now because I'm aware that I want to leave some time for questions and for discussion at the end, but I just want to tell you a few research frontiers that we've been working on, or findings we've had with trying to explore this technology for these kind of applications ourselves in our own hands. And here you see the steps involved in a systematic review, and the most easiest to automate is the step of finding and selecting the studies to include. So I'll talk about that first. The second step I'll talk about is extracting the data from the study to put into your sort of overarching database or integrated evidence synthesis. And then finally, I'll conclude with a little bit of speculation or a pilot research study we're doing about the whole problem of really formulating or understanding the evidence as a whole sufficiently to formulate a good question at all, which requires a kind of different way of looking at the research literature. So this is quite a straightforward task, the task of selecting studies for including in the systematic review, title and abstract screening. I say straightforward just because you typically have all the information that you want to use because you're sort of having a very well-defined, you can search these databases of literature, you can extract thousands or whatever of papers that match a certain keyword list in your research question, and you can define, okay, I'm interested in studies that have exercise, I'm interested in studies that have psychotherapy, and then you can do this, you can set up this automation task in a quite straightforward way. So it's not that it's easy, it's just that it's relatively easy to specify and to try and automate. And this paper was published in the journal Systematic Reviews. And what we did there is we just tried to apply several language models to this problem of automating the decision whether a given paper, as described by a title and abstract, should be included in a given systematic review as described by a set of inclusion and exclusion criteria. And we set this up in such a way that if you specify the inclusion and exclusion criteria, you then ask the model, please say on a scale from 1 to 5 or from 1 to 10 or whatever, whether you think this title and abstract are relevant given this inclusion and exclusion criteria. So it was a single prompt for the whole review for each title and abstract. And this, you could imagine setting this up differently. I'm aware of other people or other approaches, and we even used other approaches in different studies where you ask each inclusion or exclusion criteria separately, right? And then you get a whole lot of yeses and nos for different questions, and afterwards you try and integrate it. But here we were using a kind of an all-in-one approach. So in order to evaluate, we focused on open models. Here, maybe most of you probably know there are kind of different types of offering of language models. Some of them are commercial and you can access the model via an API or something, but you can't run it yourself on your own machine because you can't download the model itself. And then on the other hand, you have open models. There's a whole thriving community of sharing and improving open models, and there you can actually download the model itself and run it on your own machine. You don't have to though, because there are also APIs where you can access and run open models. But it's an important distinction if you work in healthcare settings, because often in healthcare settings, you need to keep the data private, not for this kind of task, but for other tasks. So for that reason, we're always interested in my group in working on open models as far as possible. So for this project, we decided at that time to evaluate these 4 open models, and we took a whole lot of existing data sets of systematic reviews where the sort of inclusion papers were known. So we could evaluate whether the model would give the same output as a human would. But we also, because the challenge with these kind of models is that they have seen all the studies before. So you have some kind of bias because even though it's maybe a very small point in the model's training data, all existing data sets you can assume are in the model's training data. And for that reason, we also created a brand new data set for this study where we did the evaluation of 500 papers and decided whether or not they should be included. So here you see the results, and it's a little bit not a great visualization, but what you're looking at here is when the model sort of said yes to a paper, it should say yes to, and then did it find all the papers that it should find. So basically you have two possibilities. You could have like very specific yeses, but then you're missing a lot of papers that you should include, or you could have very broad ranging yeses, you don't miss any papers, but you nevertheless end up with far too many because in the end, many of them were not relevant, right? So the objective for this was to emphasize the sensitivity, so to make sure we did not miss any relevant papers, which is why we set the threshold so that we get most of the results on or close to 100% sensitivity. So that means that really what we're asking ourselves is how many, if we had at or close to 100% sensitivity, how much specificity could we achieve while keeping that sensitivity so high? And so you see the best performing model on average across the different tasks and questions that we provide was this Mixtral of the ones that we tested at that time. I should say that every model we tested in this study, which was done not even a year ago, was by now completely out of date. That's the nature of working in this area. We get a new model every 2 or 3 months, and then all of our papers are completely out of date. But I like to think that the generalizable learnings that we get from these studies are nevertheless helpful. And one of the generalizable learnings that we got from this study, which you can clearly see, is that different data sets have different performance profiles. And this, I think, is completely generalizable, and other papers have shown the same thing. Depending on the nature of the question and the nature of the, let's say, the ontology or the conceptual structure of the domain, it might be easier or harder to decide whether a given paper belongs in a given systematic review. And I think that's a very important take-home message, because what it means is that you can't really predict in a very strong and a confident way how well a system will do for a future systematic review, for a future topic, for a future domain, and so on. You always have to evaluate again how automation will work on that particular aspect. All right, so another thing we've been working on is data extraction. This particular paper, which is not yet published, this is just a preprint, it is under review at the moment, developed a system to extract categorical information or information which could be bullied into being categorical from whatsoever text. And here the key innovation is that the system is set up in a way to kind of restrict the output options. There are various different libraries which allow you to do this. I don't go into the details, but basically it involves looking at, because your language model gives you probabilities of a next word or a next sort of predicted answer to your question. And these constraining approaches basically ignore not matching outputs and then just look at which is the most likely of the possibly matching categorical outputs, if any, above some threshold. So this is really good because it means you sort of you throw away irrelevant or completely nonsensical or not matching. You basically can build in a constrained ontology from the get-go. And I think we will see more and more of this kind of implementation in the future. Coming again to the results, this is again a suboptimal presentation, but what we see here are results 4 different types of questions which we applied. And actually, in this case, they were all oncology related, so cancer related. And again, we see a kind of clear pattern that depending on the question, the nature of the question being asked, we see a different performance from the models. And I think this, in most cases, the performance was good enough that you could really use this system to automate the extraction of that type of data, but then in some cases not. And we need to know, right? We need to check and know every time. And now finally, just as a last little sideline, I want to talk about slightly more interesting. So one of the things which these types of models are being used for is really a lot. People are sort of like engaging with the model, discussing with the model, saying, hey, how could we approach this thing? Or what might be an interesting research question in this area? And this is something where I think this technology, the fact that it's interactive and it behaves human-like to an interaction partner, creates all kind of interesting possibilities and potentially philosophical challenges. But I won't go into too many of those now. What I wanted to talk about, the idea of sort of how do we take a look at the whole overview of research in a given area and then figure out what might be a promising research direction for the future, is a question which the funders are very interested in having as answers. So this particular study funded by the Wellcome Trust, and the Wellcome Trust asked us, could we have a look at whether some kind of language or technology related system could be developed which would give a clue as to what might be a future area or future promising research directions? And so in order to try and answer this question, or to see how well automation could answer this question, we thought, well, at least what we can do is we can track mentions of topics, and research questions may arise within topics. We can track these over time. This is something we can do, right? You just need to be able to sort of, okay, define a topic and then track the topic mentioning over time, and then perhaps identify sudden changes in a level of interest in a research topic at a point in time. And maybe this could be sparked by one paper showing a kind of new direction, which then explodes into an area of research, or it could be sparked by an external event. And then if you've got these things, you sort of, okay, we've identified there is something, a topic that is having a lot of interest at the moment. Maybe then we could go and look within that topic to identify research gaps or research questions or research directions within that topic. So in order to identify the topics, we used a language model based approach called neural topic modeling. What this does is it embeds a whole lot of documents into a kind of latent space, into a mathematical representation, and then clusters that mathematical representation in order to chunk up the literature into different topics based on their kind of the meaning behind the words that are used. This is an established method. We didn't invent this method, but it's particularly flexible, which makes it a good way of doing this for the mental health literature, where meanings are very context dependent. And then you see, okay, we took our corpus of mental health literature, and you see you get out a certain number of topics. It depends on how large or how small you define the topics that you want to be. This is a parameter of the approach. You can decide. That time when I ran it, it was 1,200 topics. I think now I'm working with 950 in the same data set because I made the topics a little bit bigger, but you can see some flexibility there. And the topics are also hierarchical. You can have a big topic and then some very specific topics within that. And then to get an idea of how these topics evolve over time, we did aggregation. So what we're aggregating here is the mention of a topic inside a given paper, and paper is just a title and an abstract. So you can aggregate weekly, and it looks like this, and you can see that this is a very noisy and very difficult to get any information out of this. You can aggregate it monthly, And you can see at the monthly level of aggregation, you do start to see what I think are meaningful signals about how these topics are behaving over time. You can also aggregate it yearly, and I think at the yearly level, you've lost most of the interesting signal about how they are behaving over time, except for the very largest of signals. And here, of course, you see the very largest of signals, that COVID-19 suddenly emerged as a topic in the published research literature in early 2020. And this would be a kind of positive control for the approach that we can pick up relevant topics. Okay, so then there's a kind of challenge. How do we identify relevant surges in interest in a topic? What does that even mean? There have been some approaches which have tried to do something like this in the genomics or the biomedical literature, and they took different strategies. So we looked a lot at these plots, at these kind of histories of what was happening over time, and we sort of decided, okay, this is the kind of thing we want to pick up. We want to pick up the change in interest that we see here in early 2020 for COVID, but we do not want to pick up the kind of stabilizing parts where the topic, it still has a lot of interest, but it doesn't any longer have a sort of new interest. It's just a stable level of interest. So, and here's an example from our mental health related topics. So this topic, first episode, psychosis. Each topic is identified by a whole lot of words, but we give it a short, meaningful name. You can see here there are on average 20 or so publications in our corpus every month on this topic, and regular high interest, but no specific, changes really in that level of interest. So if we took, so what you see here, the orange line is a kind of a fitted predictive line over this time series data set. And we've defined topic trendiness in terms of the divergence of the actual prediction, of the actual mentions of the topic relative to this fitted predictive line. And you see here a kind of example where you have a strong signal, and this was for postpartum mental health, and a weak signal, and it's weaker because there's less of the months that are over the prediction and only a few sort of in that period. And this weaker one, problematic social media use, might be coming even more strong now. All right, so I skip over that. I think this sort of footnotes to the usability of language models, which I always enjoy and which I always find so fun to put into presentations, but we might not have enough time for. Just a reminder that what language models do is a kind of approximation, not necessarily a definite and clear understanding. And these are two of my favorite examples. These are generated images, and here's the prompt: two people go for a walk by a lake, and here they are having a nice walking on the water effect. And this one is just the best. So a room that does not have an elephant in it. And you see here, it does this every time. I love it. It's like, does such a beautiful elephant because it can't process the knot in the right way. But another point I wanted to mention, particularly for the Swiss context, is that we've seen that also, and others have seen, that also the performance of this technology varies not only by model, not only by topic, but also by language, right? So for medically related questions, at least the GPT models and some other models do better in German. But some models, this model Yi, which is a Chinese developed model, does better in French. So you should know, depending on your language of interaction, which one you want to work in. But I wanted to come to the end so that we still had some time for questions. And the main point I wanted to make is that we have this powerful technology, but it's not exact, and we have to evaluate it carefully for every use case and still build those ontologies where we capture those shared human consensuses about what different categories matter and how we want to apply those categories to data. And then we can kind of harness these powerful automation technologies in the right way? I stop there, and thank you for your questions.